this is Jimin LEE from the KGSEA Math Circle, and this Open Schools lecture, I would like to go through the topic of systems of linear equations and matrices. Now let's consider the following system of equation. A common method to solve a system like this would be to use the method of substitution or elimination, and to figure out the value of each variable one by one. However, a major drawback of such methods is that it becomes increasingly complex and computationally intensive as the number of variables or the equation increase. Today, I would like to introduce an alternative method to solving these systems of linear equation using matrix operations, which is by determining the reduced row echelon form of a given system of equation. First of all, we need to understand the basic operations that can be carried out on a matrix and how it can be used to represent a system of equation. When we write the system in the matrix form, we organize all the coefficients into a rectangular array and include the constants as an extra column. And this is called an augmented matrix, which is defined as the matrix formed by appending the columns of two matrices, typically between a coefficient matrix like this and a constant vector. For the system above, each row represents an equation system, and each column represents a variable, with a vertical bar separating the constants on the right-hand side. Once in this form, we can freely carry out three types of fundamental row operations that do not change the solution of the system. First, we can swap two rows to reposition the equation for convenience. Second, we can also multiply a row by a non-zero scalar constant to scale it. Third, we can also add or subtract a multiple of one row to another row to eliminate variables. And many people might be familiar with these kind of operations from using the elimination method in the conventional method of solving simultaneous equations. By applying this operation repeatedly, we can gradually transform the augmented matrix into what is called a reduced row echelon form, where we can directly read the solution of the system. Before proceeding to the reduced row echelon form, let's first look at what is called a row echelon form. A row echelon form is a matrix structure that satisfies the following rules. The pivot, which is the first non-zero entry in the given row, is strictly to the right of the pivot of the entry of the row above it. All entries below a leading entry are zero, and all zero rows sit at the bottom. And combining these three rules produce a unique staircase shape to the leading entries of row echelon form. These rules can be a bit obscure when explained in words, so let's look at some examples. The first example demonstrates the clear staircase pattern in row echelon forms. The pivot of the first row is in column 1, the second row in column 2, and the third row in column 3, such that the pivot of each row is located at the column on the right side of the previous row. The second example demonstrates how an all zero row should appear in row echelon form, which is at the very bottom row of the matrix since it does not have a pivot entry. The third matrix shows how the conditions can be satisfied when there are more columns than rows. The pivot entry doesn't necessarily have to be adjacent to the row above it, but just has to be on the right side. And deducing the REF is useful because it puts the system into a form where back substitution is quite straightforward. You solve the equation of the bottom row first, and determine the value of a variable, and substitute upward to determine the value of each variable one by one. But the issue of REF is that it requires additional computation, and it's not unique for each matrices. And multiple valid REFs can exist for the same system of equation, which makes it less clean as a final answer. That's where we can use what is called a reduced row echelon form. So these, in addition to the three conditions that we previously had for the row echelon form, to make a matrix into reduced row echelon form has additional constraints. First, every leading entry has to take exactly the value of 1, which we call a pivot, and in addition to the entries below the pivot being 0, all entries above each pivot also have to be 0. Like we did before, let's look at some more examples. The first example is a REF because all pivots take the value of 1, and all entries above and below each pivot is set to 0, so all conditions are satisfied. The second example also satisfies all pivot conditions, with the leading ones being in column 1, 3, and 4, and all entries above and below that column are set to 0. Additionally, the all zero row is correctly placed at the very bottom according to the predetermined rules. And these are some examples of matrices that are not in proper RREF form. The first example is not in reduced row echelon form, as the pivot of the second row is not equal to 1. The second example is also not RREF, as there is a non-zero entry of 5 above the pivot of row 2 in column 2. The third example is not an RREF, as the rows are not ordered by leading ones, and the pivot of row 2 is on the left of row 1's pivot. The last example is also not an RREF, as the all zero row is not correctly placed at the bottom of the matrix, but instead is in between rows that have pivots. Unlike row echelon forms, reduced row echelon forms are unique to each matrix. Regardless of the process you choose, you'll always arrive at the same RREF form if you start from the same matrix. To determine the RREF of a given matrix, we must go through a process called the Gauss-Jordan elimination, which is an algorithm to create RREF matrices using elementary row operations of switching, multiplying, and adding that I explained before. So let's say we have a system like this. Based on the coefficients and constants, we can convert the system of equation into an augmented matrix as follows. And recall the rule of REF that the pivot, or the leading element of each row, has to take the value of 1. We look at the first row in column 1, and we can see that the pivot is already set to 1. To ensure that all other entries of column 1 are set to 0 to adhere to the rules of REF, we eliminate the first column by subtracting the multiples of row 1 from row 2 and 3. From row 2, we take away 2 times row 1. From row 3, we take away row 1. This gives us this matrix on the right. Let's now move on to the second row. Notice that the current pivot element has the value of -3, and we want to set it to 1. We divide all elements in row 2 by -3, which gives us this matrix on the right side. Now that we have the pivot of row 2 set as 1 in column 2, we carry out the similar process of elimination to zero out the elements of other rows in column 2. From both row 1 and 3, we take away the value of row 2, which yields the following matrix. We carry out the same process for row 3 as well, and we end up with the following matrix in reduced row echelon form. The pivot elements of 1 in each row forms this staircase pattern, and if we look at all the 0 entries, we can determine that the following matrix follows the conditions for REF. Now, converting this augmented matrix back into linear equation gives the solution to the system equation, with x being 15/7, y also being 15/7, and z being 18/7. Unlike row echelon forms where back substitution were needed, reduced row echelon form directly provides the solution. Now that we know how to determine the REF from a system of equation, let's return back to our initial system that we had in our intro. By expressing the system in the form of an augmented matrix, we can apply a similar process of Gauss-Jordan elimination on a 4x4 matrix to solve the following system. Now let's convert the system into an augmented matrix, and we begin with the first pivot in row 1, column 1. This is already set to 1, and our goal is to eliminate all other entries in column 1. So we eliminate the entries by subtracting multiples of row 1 from the other remaining rows. So row 2 becomes row 2 minus 2 times row 1, row 3 becomes row 3 minus 3 times row 1, and row 4 becomes row 4 minus row 1. This gives us this matrix on the right, where all non-pivot entries in column 1 are cleared out to be 0. Next, we move on to second pivot in row 2. To make it into a 1, we divide row 2 by -3. And now we eliminate all non-pivot entries in column 2 from other rows as well. Row 1 becomes row 1 minus row 2, row 3 becomes row 3 plus row 2, and row 4 becomes row 4 plus 2 times row 2. And this gives the following matrix on the right. Next, we repeat the same process on the third pivot in row 3. We first convert the pivot into 1 by multiplying row 3 by 3/11 and subtracting its multiple from row 1, 2, and 4. This gives us this matrix on the right. And finally, we make the fourth pivot equal to 1 by multiplying row 4 by 11 over 48, and eliminate entries above based on the final pivot, which gives the final answer on the matrix in reduced row echelon form. Like we did before, we can observe the clear staircase pattern and all pivot entries being set to 1. And converting this result back into equation form directly gives us the answer of x equals 15 over 4, y equals 7 over 3, z equals 19 over 12, and w equals 31 over 12. And this is how you can use the Gauss-Jordan elimination and reduced row echelon form to solve the system of equations. And let's look more closely into how the end result of the RREF connects to the type of solution a system can have. The example we looked at previously has a unique solution. This occurs if every row has its own pivot, such that each one of the augmented values on the right side of the matrix can be assigned to each of the distinct variables. Alternatively, a system can also have infinite numbers of solutions. This occurs when at least one variable of a column has no pivot, indicating that it is a free variable. A free variable can take any value, and to other values can be expressed in terms of it. Because of this, the system becomes dependent, meaning that at least one equation can be written as a combination of the others. For example, in this matrix, column 2 of this matrix doesn't have any pivot values located in it, so y can take any values without constraints. Lastly, a system can also have no solution if there is a contradiction, which means that if at least one all-zero row has a corresponding non-zero constant term on the right, this indicates that the system is inconsistent and therefore has no solution. For example, since the last row of this matrix states that 0x plus 0y plus 0z is equal to 1, there's no values of x, y, and z that can satisfy the system. To summarize, in this presentation, we went over the following topics, which is expressing systems of linear equation in augmented matrices, basic matrix row operations, row echelon form, reduced row echelon form, and how to use the Gauss-Jordan elimination to create a matrix in RREF form, as well as interpreting RREF as solutions to a system of equation. And that's the end of my presentation, and thank you for listening.